Welcome to episode 18 of the Head in the Clouds video series. I am Ken Hartman, a SANS certified instructor and content creator for the SANS Cloud Security Curriculum. Today's episode is titled Benchmarking AWS Flow Logs. In many of the courses in the SANS Cloud Security Curriculum, we will have one or more labs that involves flow logs. However, a portion of the lab time is spent waiting for the flow logs to get provisioned. It's kind of like watching and waiting for the water to boil. Then, once the flow logs are provisioned, it takes time for the measured traffic to show up. Therefore, I thought it'd be very interesting to determine what one should expect to wait via experimentation and observation. And along the way, I made some very interesting discoveries, and I cannot wait to show them to you. Anytime we use a tool, technique, or service, we should be aware of its limitations and possible pitfalls. As such, here are the objectives for today. Experimentally determine the typical time to provision flow logs to an S3 bucket. Experimentally determine the typical time to provision flow logs to a CloudWatch logs group. Experimentally determine the typical delay for ongoing traffic to be captured in the flow log record. And then we want to contemplate the implications of our findings. For this episode, we will assume that you have an AWS EC2 virtual machine running in a VPC that has a name tag of HITC-VPC. The T2 microtype that is in the free tier will do just fine. I do recommend that you use an Ubuntu 20.04 AMI for your region, as this will allow me to provide you with the exact commands to install some additional software later in this episode. I used Terraform to deploy my environment as described in the Head in the Clouds episode titled Episode 10, Demonstration of Terraform Modules, Deploy a Virtual Machine in AWS, Azure, and GCP all at once, as I had originally planned to benchmark all three cloud service providers. However, as I got deeper and deeper into my research into AWS flow logs, I decided to stay focused on just AWS and may circle back to Azure and GCP flow logs in one or more future episodes. In this episode, we will be making extensive use of the AWS command line interface. This has two benefits. It will make it very easy for you to reproduce my work, and second of all, it will allow us to measure the time that it takes for things to happen. The machine on which you're running your CLI commands will need the JQ utility in addition to the AWS command line interface. Okay, let's get into Objective 1, experimentally determine the typical time to provision flow logs to an S3 bucket. To start with, we will need to set some variables that will be used by our various commands. We generate a unique ID to ensure that the S3 bucket that we create is unique. Linux has a variable called $random that we can use for this purpose. The YYYY, MM, and DD are captured so that we can look into the bucket for our data. Lastly, we'll use a trick from stackoverflow.com to get the region, as yours may be different from mine. Next, we'll create a variety of helper commands. To get the VPC ID of the VPC that is named HITC-VPC, we can use. Next, we need to create an S3 bucket to receive our flow logs. Our next task is to make sure that we have the command to set the flow logs for the VPC and to send them to the S3 bucket. Having done that, we may find it helpful to be able to describe the flow logs for the VPC in question. Next, we need to be able to delete the flow logs that we just created. To do this, we need to know the flow log ID. To verify the presence of a flow log, we will need to be able to drill deep into the S3 bucket, and this is facilitated by the variables that we set earlier. We will also need the ability to empty the bucket between successive iterations of our test. It's also a good idea to remove the bucket when we are all done with our testing. Now that we've got our helper scripts figured out and tested, we need to generate some traffic to get captured by our flow log. SSH into your EC2 instance and run the following command. Note that I selected Cloudflare as the target, as they're big enough that this would not be considered abusive, and by sending the traffic to port 81, the retries will keep working until exhausted after 20 attempts, and then it will start over after waiting 20 seconds. Anything that repetitively generates traffic will work fine here. With that done, we can now measure the time between the provisioning of the flow log until the first flow log record appears in S3. Every 20 seconds, we will check the S3 bucket to see if the flow log showed up yet. Our test checks to see if the length of the response of the AWS S3ls command is 0. Once there is a flow log record in the bucket, the infinite loop will exit, and we subtract the start time from the end time. Because we're working in epoch time, it makes this very easy. Note, the script also assumes that the S3 bucket exists, but it is empty before we run it. While the script executes, it will print a dot to standard out every 20 seconds. And when it's done, the output of the script will look like this. Okay, 772 seconds is 12.87 minutes. We now have our test 1 measurement. Note that this can be off by 20 seconds due to the sleep timer, which of course could be removed. To repeat the test, we need to delete the flow log and empty the S3 bucket, but leave the S3 bucket in place. This table shows the results of repeating the test 3 more times. Wow, it can take 16 minutes to get your first flow logs. So what is up with this? Well, the catchphrase that the cloud service providers use is, air quotes, eventual consistency. We know that the big guys use queuing and focus intently on optimization, so I'm guessing that it is for these reasons that there is a provisioning delay. Now that we've obtained our results, make sure you delete the flow log and empty the bucket again using the last set of commands, and then remove the bucket as we no longer need it. Now let's take a look at flow logs sent to CloudWatch logs. First, we need to create the CloudWatch logs group. And here's the corresponding command to delete the log group. Next, we need to create the CloudWatch logs role. To do this, we'll create the trust policy JSON file, the permissions policy JSON file, and then attach them to a new role. We create the trust policy JSON file, and I like to use the here doc technique, so this way everything can be scripted. We will also create the permissions policy JSON file. Next, run the following commands to create the policies and then the role. With our setup for test 2 in place, we can now conduct the test. This test checks to see if the length of the response of the AWS logs describe log streams command is 0. Once there is a flow log in CloudWatch logs, the infinite loop will exit and we subtract the start time from the end time as before. Note that this assumes that the CloudWatch log group exists but is empty. To rerun the test, delete the flow log and reset the CloudWatch logs group by deleting it and recreating it. And then when we're all done, we can run the following commands to delete the role and the associated policy, but hold off for now as we will need this role for test 3. Here's a table of results for running the test 2 4 different times. We can see that this is much better, but it can still take up to 10 minutes and is somewhat variable. Now on to what is probably the most interesting and has the biggest implications for security monitoring. We want to know how long it will take for traffic that occurs in my VPC to show up as recorded in my flow logs. In other words, I want to know how much lag there is in any detective control that I implement that is based on flow logs. The security implications of this are fairly significant. Wouldn't it be great to timestamp a packet, send it across the virtual network of our VPC, look at the packet in CloudWatch logs and determine how much delay there was between the time the packet was sent and when it was recorded. That'd be fantastic. The only problem is that the flow log contains only metadata and not any payload. Here's a screenshot of what we have to work with. As it turns out, about the only thing that we have to fiddle with is the source port and the destination port. So I will use the source port to encode the timestamp and send it to an unchanging port 7777 TCP, at a target IP address outside of my VPC. Will this work? Well, let's do some math here. We know that there are 65,536 possible TCP ports. That's 2 to the power of 16. If we send one packet per second from a different port, we could do that for 1,092 minutes. Or converting that to hours, we get 18 hours. Hence, we can send traffic at the rate of 1 packet per second from a unique source port for over 18 hours before using up all possible TCP ports. To calculate which port to use, we will take the current epoch time and divide it by 65,536, and then take the integer portion of the remainder and use that for the source port. The math function that returns the remainder is called modulo, and it is represented by a % sign in Python. To convert back to the epoch time from the source port, take the current epoch time and divide it by 65,536, and then keep the quotient portion. Divide the source port by 65,536 and take that result and add it to the quotient. Multiply the new total by 65,536, and the new result is the epoch time of when the data was sent. Now, this conversion assumes that the current epoch time is within the 18-hour window represented by the source port value. To generate 1 packet per second with an ever-increasing source port that represents the time that the packet was sent, I used Scapy. Scapy is written as a Python module and is ideal for programmatically crafting packets. As we will be running Scapy on our EC2 instance to send traffic out of our VPC, we need to install Scapy, its dependencies, and the additional modules my Python program will use. Note that using sudo with pip to install software is generally a bad idea. However, in this case, Scapy needs to be able to run as root to be able to send packets, and we're going to destroy our EC2 instance at the end of this experimentation anyway. To launch Scapy, just type sudo scapy at the Ubuntu command line as shown. I set up a virtual machine in another VPC with the security group set to allow inbound TCP port 7777 from the system with Scapy installed. As a test, I'm running TCP dump on the target machine using the command shown. Next, use Scapy to send the target a packet, entering the following commands at the Scapy IPython prompt. Substitute my target IP address for the one that you will be using. And the result should look like sent 1 packets. Note that if you get an operation not permitted error, you forgot to run Scapy as root. To exit IPython back to the Ubuntu command line, we can use exit. Looking over at the target system, we can see that TCP dump captured the following 2 records. We sent a TCP SYN packet, and a reset packet was sent back because there was not a service listening on port 7777. Okay, so now that we know the Scapy commands to craft a packet, we can write a program to determine the source port to use and to craft the packet and send it. We can also prove that the packet was received by the target system and see the timestamp printed to standard out by TCP dump. The program to generate the traffic is called, simply enough, generate test traffic.py, and can be downloaded from my Git repo. Copy this program to the EC2 instance that has SCAPI installed. Run the program as root using sudo python 3 generate test traffic.py. Once the program runs, it will ask 4 questions as shown below and then start to send packets at a rate of 1 per second. Here's another example where I ran the generate test traffic.py program. I'm calling the log file test3a and provided 35.168.8.211 as the target IP. But again, be sure to use the IP address of the target that you set up and that has TCP dump listening. I started the program at 1900 hours UTC simply because that was on the hour, and I wanted it to run 3 hours, ending at 2200. The program uses UTC because that is the time zone that AWS uses for all of its cloud services, including EC2. While I was waiting for the traffic generation to start, I set up the TCP dump on the target system, this time capturing the packets to a file. The generate test traffic.py script created a log, which I named test3a.csv. Note that the script adds the CSV extension to the file name. The top 10 rows of the file are shown here. We can look at the top 10 packets received by the target system using the TCP dump command as shown. And this produces the following output. We can extract the 2 critical data elements from this packet capture using the command shown on screen. Great, everything correlates. Now let's write the whole packet to a file. We will save test3a.log for later, as it will come in handy. The CloudWatch Logs web console is a great tool to slice and dice log data. Paste in the following query. Be sure to set the time filter in the upper top corner to include the window in which the packets were sent. Looking at the output, we see that AWS provides 2 fields, at ingestion time and at timestamp. So we can calculate the ingestion delay seconds by converting both time values to epoch time and subtracting them. But how accurate is the timestamp? Well, we can use the CloudWatch Logs query language to calculate a sent time epoch based on the source port. We can also convert that to sent time so it is human readable. If we subtract the sent time epoch from the timestamp epoch, we get the timestamp delay seconds. Disregard the first record, as that was captured when I demonstrated how to use SCAPI with IPython using an arbitrary source port. I generated the traffic using the Python script a few hours beforehand, and that explains the chronology of this particular timestamp. This record will be removed from the downloaded dataset. Another thing that you may have noticed in the screenshot is that the first source port is 4184, which is 40 seconds after we sent the packet with source port 4144. Very interesting. It looks like we have negative delays, or to phrase it more accurately, the at timestamp value generated by AWS has an error that fluctuates within a range. Use the Exports Results button to save the file as logs insights results.csv. Since we see that we have an ingest delay and a timestamp error, it would be good to look at this data graphically. Toward that end, I have created a Python program called plotobservations.py, which can be downloaded from my GitHub repo. Copy this program to the EC2 instance that has SCAPI installed because it has the other dependencies that this Python program will need, and then run the program using Python 3 plotobservations.py. The program will read the log insights results CSV file and will generate the 4 plots shown below. Now let's talk about each one of these in turn. Plot 1 shows packets 1000 to 2000 and gives a good feel for the shape of the data. We can see a very uniform pattern with both the error and the ingest delay seconds. Plot 2 shows it a little bit closer, zoom, packets 1020 to 1200. And then plot 3 shows the first 10,000 packets. It's limited to the first 10,000 packets because that's what we are able to get out of CloudWatch logs insights. And then the fourth one is the seconds between missing data. You probably noticed that there was a chart on each of the 3 previous plots that showed data as missing. We're going to take a look at that in a little bit closer detail coming up. I saved the charts generated from data captured in the exact same manner 24 hours prior to this set, and these are shown next for comparison purposes. As far as observations go, well, regarding ingest delay, we can see the ingest delay varies from a little over 60 seconds to almost 11 minutes every 10 minutes. Note that when we configured the flow logs, we used a setting of max aggregation interval set to 600. This test should be repeated using a max aggregation interval of 60 seconds to measure the impact on ingest delay. For timestamp error seconds, this is calculated by subtracting the send time epoch from the timestamp epoch. Chronologically, the send time epoch should occur first, as that is the timestamp of when SCAPI sent the packet. Similarly, the timestamp epoch is when the VPC flow log system detects the packet on the virtual network. I expected the error to be within milliseconds, but not almost a whole minute off. I'm not sure how to explain this. At first, I thought it might be a math error on my part or a bug in my function, but we can take a look at a single packet as it was recorded in the flow log, sent by SCAPI, and recorded by TCP dump at the target system. We can use grep to search for -58, which happens to be the greatest error in log insights results.csv, and generate the following table. And now that we've identified the first 5 packets with the highest error, we can look for those packets in the log generated by SCAPI using grep again. We can see that the send time epoch, as calculated by my CloudWatch logs query, is performed correctly as it matches the epoch time as logged by SCAPI. For completeness, now let's take a look at TCP dump. As expected, we can see that the epoch time recorded by TCP dump matches the other observations. Looking at the missing data plots in the figures above, I initially was concerned. Is the VPC dropping packets? What's going on here? To investigate, I tweaked the plot observations.py to generate the delta plot to show the periodicity of the missing data, as well as to output the source ports for which data is missing. That output is shown here. I also had plot observations.py write the ports to a file called missing source ports.csv so that we can grep for them. None of the missing source ports were logged by SCAPI. Well, the good news is that the VPC network did not drop any packets because all the packets sent had been accounted for. The bad news is that there is a bug in generate test traffic.py that occurs about every 195 seconds. I suspect that it is an issue with my generate traffic function, most likely due to inaccuracies with time.sleep. That compounded with variations in the amount of time it might take SCAPI to write the packet out to the network. Okay, before we wrap up, let's contemplate the implications of our findings. Tests 1 and 2 demonstrate that we need to budget ample time, at least 16 minutes, to allow AWS to provision the flow logs. We observed that the flow logs sent to CloudWatch logs provision faster than logs sent to an S3 bucket. Test 3 demonstrated that with a max aggregation interval set to 600, it is possible to see an ingestion delay of up to 10.42 minutes, and that is a function of how long ago the last aggregation occurred. The minimum ingestion delay was 1.26 minutes, and lots of bad stuff could be detected late if you're expecting to use flow logs for real-time detection. I think that AWS would tell you, well, that is not the use case that flow logs were designed for. Instead, use something like a web application firewall. We observed an unaccounted for error in the @timestamp field generated by CloudWatch Logs Insights of +1 to -60 seconds during our test and +60 to -58 during a previous test. This demonstrates the value of benchmarking critical security systems. In this experiment, we demonstrated a novel technique for timestamping packets that will be reduced to a flow log by using the source port field. We showed how to verify the accuracy of the technique by comparing the epoch time calculated from the source port with the time logged by TCP dump. We also demonstrated how to identify any missing packets using this technique, and in the process, identified a minor bug in generate test traffic.py that caused a packet not to be sent about every 195 seconds. This demonstrates, again, the importance of understanding the limitations of the security tools that we use. At some point, I will circle back and fix this bug. Remember that the limited amount of testing that was performed is not sufficient to draw too many conclusions. Tests 1 and 2 should be repeated multiple times at different times of day, over the course of several days in different regions to get more precise statistics. Test 3 should be repeated multiple times and should consider the impact of changing the max aggregation interval setting. The more the testing process is automated, the lower the burden of repeating each test. But I think I've taken this little experiment far enough for now. Wow, we have covered quite a bit in this episode. We made extensive use of the AWS CLI. We used a bash while loop to time AWS CLI calls. We crafted packets using SCAPI and read those packets using TCP dump. We also created a fairly sophisticated CloudWatch Logs Insights query and learned how to use Python to visualize data. To learn more about TCP dump, SCAPI, and packet crafting, check out SANS Security 503, Intrusion Analysis in Depth. To learn more about using Python to create security tools like generate test traffic.py, consider SANS Sec 573, Automating Information Security with Python. If you have thoughts or comments on today's episode, feel free to chime in on the comments for this YouTube video. If you appreciate this video and you want to see more like it, well, be sure to give it a thumbs up. Stay tuned for another installment of Head in the Clouds as announcements of new episodes are made on the SANS Cloud Security Twitter feed. Meanwhile, be sure to check out the other great videos on the SANS Cloud Security YouTube channel. Take care.